All right, so now let's go ahead and talk about blood flow to organs and tissues. We'll talk about coronary arteries, so like looking at how the heart's blood flow works, skeletal muscle, the brain, and the skin. Those are really the main ones we're talking about here. So let's go ahead and talk about this. So we're looking at basically how blood flows when we're looking at heavy exercise versus rest. All right, and we're looking at how much blood per minute in comparing the two. But it's really variable, right? So if we're looking at, if we're looking at rest, let's talk about rest first, because that makes more sense. At rest, if we're accounting for all the blood, the 5 liters that are being pumped through per minute, we're seeing that a good chunk of that is going to the digestive system. A small bit is going to the heart. About the fifth is going to the kidneys. A small amount to the bones. Right, almost a fifth is going to the brain, a little bit to the skin, and a reasonable chunk, about another fifth, to the muscles, right, when we're resting. So it's fairly evenly distributed, right? When we look at exercise, because again, this is, while we're exercising, the metabolic needs of different organs is going to change drastically. So we see that we are shifting blood away from the digestive system. The heart is getting the same amount. The kidneys are getting way less percentage-wise. Bones are getting less. The brain is getting less. But the skin and the muscles are getting the bulk of it. About 4/5 of the blood is going towards the skin and the muscles, which it makes sense because at that point during exercise, the part of the body that is most metabolically demanding is the muscle. So that makes sense, right? But we're changing it in response to what we're doing, right? When we're at rest and the muscles are not as metabolically expensive, sure, we can, shift that to other things. But let's talk about blood flow to the organs and tissues, starting with the heart and looking at coronary arteries. So the coronary arteries are basically going to be servicing the heart, pumping blood into all these capillaries that we find in the heart tissue, in the cardiac muscle. Because cardiac tissue is metabolically expensive, right? There's lots of mitochondria, there's lots of enzymes, because the heart has to pump 24/7, right? So it makes sense that this active tissue needs a lot of energy, needs a lot of blood, right? It needs very detailed service. When we look at exercise, the coronary arteries are going to go from about 80 milliliters a minute to about 400 milliliters a minute for every 100 grams of tissue. Right? Now, the one thing that's different here is that blood flow to the muscle tissue in the heart is restricted to systole, right? So during diastole, we don't have blood flow. It's only flowing when the ventricles are actively contracting, all right? And that's because we're linked right to that artery, or right to that aorta, right? The blood is fresh from the ventricles, basically. And that means we have a lot of myoglobin to store oxygen and whatnot for the time between those ventricles contracting. So we have to kind of actively prepare for that time in between contractions by using myoglobin to store that oxygen. Things that regulate coronary blood flow, a lot of it is autonomic, right, and hormones. So norepinephrine, right, this is going to stimulate vasoconstriction, which will increase resistance. Epinephrine, which will stimulate vasodilation. This is going to decrease resistance, like during exercise. And then other things like increased CO2, increased potassium, nitric oxide. If we look at the skeletal muscles, again, this depends on whether or not we're exercising. So there's a few things that go into it. So we have an increase in cardiac output during exercise because of the autonomic nervous system, right? Cardio output, the cardiac output's going to increase a lot because we're increasing the cardiac rate. The stroke volume is going to increase because the increased venous return. The ejection fraction increases because the increased contractility. And then the metabolic vasodilation is going to cause a decrease in resistance. And we're going to basically divert blood away from the viscera and the skin. So moving blood away from like the gut, right? Moving it away from the kidneys, moving it away from the digestive system and whatnot towards the skeletal muscle when we exercise. So all these things I just listed, these are all things that happen during exercise. Now, when it comes to the changes in blood flow to the brain, blood flow to the brain increases a little bit with moderate exercise, and it decreases a little bit during intense exercise. So it generally, if we think about it, it's not changing a whole lot in terms of the actual blood output, like the actual blood flow. The percentage in terms of how much blood moves per minute, right, may drastically or look very different, but the actual number, the actual amount of blood is not really going to shift. We have auto-regulation mechanisms in place for this, like nitric oxide. But again, the blood flow to the brain is pretty constant even when blood pressure is shifting, right? Because the brain can't tolerate that variation. We need it to be consistent, and so we have mechanisms in place that even when blood pressure is changing, we are just shifting in response to that so that we can keep blood flow constant. We're not changing how much blood is flowing through at any given moment. When we look at the skin, the autonomic nervous system is the main thing kind of helping control this. Things like emotions can affect it because emotions can affect the sympathetic output, and this can cause things like blushing. Skin also is going to help with body temperature. We can regulate blood flow. We can basically shunt blood to either blood vessels that are closer to the surface or deeper, depending on temperature. So if it's warmer out, we'll shift blood towards the surface so that body heat can be dissipated off. If it's colder, we'll shift things deeper so we can retain that heat, right? So when it's really hot, we increase that blood flow to capillaries in the skin so they go up closer to the surface. The sweat, when we sweat, that also aids in heat loss. So we have this body heat that's close to the surface. The sweat is going to basically kind of pull that heat as it evaporates. So that helps us cool down. And then when we are cold, right, we decrease that blood flow to those capillaries, right? We shunt blood from arterioles like right to the venules, right, so that we can keep that blood deeper in to maintain heat. So this is just a quick, I'm not gonna read this to you because that's just kind of silly, but if you want to take a minute to take a peek at this, look at the different variables, what type of change we're gonna get, and then what the actual mechanisms are for that change are, you can go ahead and pause here and take a peek.